All right, let's talk about the tiny, basically invisible heart of, well, pretty much all modern technology. It's the one thing that makes your phone work, your computer boot up, your entire digital life even possible.
Now, seriously, think about that for a second. Is it the internet? Maybe the airplane? The light bulb? They're all incredible, right? Game changers. But here's the thing. They all rely on something even more fundamental.
Yep, you guessed it. The transistor. It's not flashy, it's usually microscopic, you can't even see it. But its impact? Oh man, it's just immeasurable. It is the ultimate unsung hero. Quietly powering, well, everything. So, what is it about this little thing that makes it so important? Well, it all boils down to one simple but, profoundly powerful function.
Okay, so picture a normal light switch, right? The one on your wall. You flick it, you physically move it, and the light turns on or off. Simple. A transistor does that exact same thing. It opens and closes a circuit. But, and this is the kicker, it does it with an electrical signal, not a physical push. And it can do it, wait for it, billions of times every single second. Mind-boggling, right?
So let's meet this electronic switch. Now, the specific kind we're going to look at today is called the bipolar junction transistor, or, BJT for short. Let's take a look at its parts. So a BJT has three main parts, or terminals. You've got the emitter, think of that as the starting line for the electricity. Then there's the collector, that's the finish line. And right in the middle, the most important part for us is the base. That's our control gate.
And this right here, this is where the magic happens. The whole point is that a tiny little electrical signal sent to that base can control a much, much larger river of electricity flowing from the emitter to the collector. It's exactly like using a tiny little key to swing open a massive floodgate. A little effort for a huge result.
Okay, so how does it actually do that? To get that, we've got to zoom in. I mean, way, way in. Deep into the tiny little piece of silicon that makes this whole thing tick.
So this silicon is treated to create two different types of material. First, you've got N-type. The N is for negative, because it's been given a bunch of spare free-roaming electrons. They're just looking for a place to go. Then you have P-type. P for positive. It's the total opposite. It has a shortage of electrons, which creates these little empty spots we call holes. Think of them as parking spaces just waiting for an electron to pull in.
So what we do is build a little sandwich. We take a thin slice of that P-type material and stick it right between two layers of N-type material. So you get N, P, N. And this specific order, this NPN sandwich, is absolutely crucial for how it works.
Okay, now check this out because this is really cool. The moment those N and P layers touch, something wild happens. All those extra electrons from the N side immediately jump over to fill the empty holes on the P side. This creates a little neutral zone right at the border, a barrier where there are no free charges left to move around. We call this the depletion region, and it basically acts like a force field, a wall that naturally stops any more electricity from flowing.
So because of that barrier, our switch is naturally set to off. No electricity can get through. So the big question is, how do we open that gate and flip the switch to on?
All right, here's how we do it. Step 1. Right now, the switch is off. That depletion region is like a wall blocking the electrons. Step 2. We apply a little signal, just a tiny positive voltage to that P-type base in the middle of our sandwich. Step 3. That tiny voltage gives the electrons the push they need. It shrinks the barrier. It basically makes that wall thinner. And finally, step 4. The switch is now on. With that barrier out of the way, a huge flood of electrons can finally race from the emitter, right through the base, and all the way to the collector. We're in business. So you see, that little tiny voltage we sent to the base, that was the key. It didn't have to power the whole thing. All it had to do was unlock the gate. And by unlocking that gate, it allowed a way bigger, more powerful current to flow through. And that, my friends, is the whole secret. It's how you get both a switch and an amplifier. It's how a tiny whisper into a microphone can be turned into a sound that fills a stadium.
Okay, so that's one switch, one single transistor. Let's zoom back out for a second. What happens when you don't just have one, but you have billions of them, all working together?
No, seriously, billions, with a B.
That little processor chip inside the very device you're watching this on right now, it has billions of these tiny, tiny switches packed inside it, and every single one of them can flick on and off at speeds that are just impossible to imagine.
And that is the final, absolutely mind-blowing piece of the puzzle. Think about it. Every photo you look at, every song you stream, every single thing your computer does, it all just boils down to billions of these simple switches flipping on or off. That's it. On and off. Ones and zeros. It's how we build this staggering, incredible digital complexity from the simplest idea imaginable, a switch.
You know, the transistor completely transformed our world in, what, less than a human lifetime? It really makes you wonder, doesn't it? What's the next tiny switch? What fundamental little invention is being cooked up in a lab right now? And what kind of world is it going to build?